In the last few videos of this lecture, the goal is going to be to understand a different kind of trigonometric integral. In the first few videos, we figured out how to integrate powers of sine times powers of cosine. Now, we want to figure out how to integrate powers of tangent times powers of secant. And our starting place is going to be remembering the derivative of tangent is secant squared, and the derivative of secant is secant times tangent. Remember, in our section on integrating powers of sine times powers of cosine, we use the identity sine squared plus cosine squared equals 1 a lot. So we want an analog of that result for tangent and secant. So starting from this identity, if we divide everything by cosine squared x, what we get is sine squared x over cosine squared x plus cosine squared x over cosine squared x equals 1 over cosine squared x. And we can rewrite this as tangent squared x plus 1 equals secant squared x. This identity is really important for this section of the course. This is something you should definitely know. I could say you should memorize it, but really if you remember sine squared plus cosine squared equals 1, and this idea of dividing everything by cosine squared, you won't forget it. So we want to integrate powers of secant times powers of tangent. Just remember there's one example we already did, which was we figured out the integral of tangent of x using u substitution is equal to the natural log of absolute value of secant of x plus c. So what I'll start with is sort of a special case where this is going to involve a trick that only works for this one example, but this one example is really key, so you should know it. So what is the integral of secant of x dx? Well, there's a trick. So let me emphasize, this is not like a general strategy. It's just a technique you should know for this one integral. If you take a function and you multiply it by 1, then you're not changing the function. It's the same function, so it has the same integral. So the idea is we're going to multiply secant of x by secant of x plus tangent of x over secant of x plus tangent of x dx. And okay, this is kind of a complicated thing to do. In the vast majority of cases, this will take your simple integral and make it worse. But in this case, it helps a lot. Because if you set u equal to the denominator, u equals secant of x plus tangent of x, then what is du? Du is equal to the derivative of secant plus the derivative of tangent dx. So it's equal to secant x tangent x plus secant squared x all dx. And what is that? That is the numerator of what's left over here. So I'm going to pause for a second and erase so we have more space, and then I'll finish the details of the rest of this integral. What were we trying to do? We were trying to compute the integral of secant x dx. So what we did was we multiplied secant of x by secant of x plus tangent of x over secant of x plus tangent of x. And then we let u equal secant of x plus tangent of x. I've rewritten everything here. I've expanded out the numerator. Here's u, here's du, just to show that what does that transform this integral into? We get exactly the integral of du over u. We know an antiderivative is natural log of absolute value of u plus c, And now we substitute back in. We get natural log of absolute value of secant of x plus tangent of x plus c. And that is our final answer for the integral of secant of x. We now understand two special cases. We know the integral of tangent of x, and we know the integral of secant of x. Now, let's break up the rest of these problems of integrating powers of tangent times powers of secant into cases based on whether those powers are even, odd, or maybe one even, one odd. So this will be just like how we broke up cases for powers of sine times powers of cosine. So let's do the first case, which is when both powers are even. Start with the first example, the integral of tangent to the 8th x times secant to the 4th x dx. And the idea is going to be just like the idea for powers of sine times powers of cosine. What we'll do is borrow a secant squared x from the powers of secant. What does that mean? So what we mean is that this integral is equal to the integral of tangent to the 8th x times secant squared x times secant squared x dx. Why is this good? Well, now we set u equal tangent of x, and du equals secant squared x dx, which we have right here. This is the secant squared that we borrowed earlier. So where does that leave us? Well, the integral we're trying to compute is now the integral of u to the 8th times secant squared x du. And this might be a problem unless we can rewrite secant squared x in terms of u. So I'll pause and then explain the rest of this integral. We're trying to understand the integral of tangent to the 8th x times secant to the 4th x. We've taken two of these secants from the secant to the 4th and put them with the dx, because now when we let u equal tangent x, du is secant squared x dx. So our integral is now u to the 8th secant squared x du. And now a major idea is that we can rewrite secant squared x in terms of u. We know secant squared x equals tan squared x plus 1, which is u squared plus 1. So this integral is equal to the integral of u to the 8th times u squared plus 1 du. We expand that out as the integral of u to the 10th plus the integral of u to the 8th du. Let me make this a little clearer. U to the 8th. And we get 1/11th u to the 11th plus 1/9 u to the 9th plus c. And we substitute back in a tangent of x everywhere that we see a u. So this problem was very similar to some of the ones that we saw when we were integrating powers of sine times powers of cosine. But instead of using an identity like cosine squared x equals 1 minus sine squared x, we use this identity that secant squared x equals tangent squared x plus 1. The important thing is that we can write even powers of secant just in terms of powers of tangent. And similarly, we can rewrite even powers of tangent just in terms of powers of secant. So I'll pause and erase, and then we'll do the next case. The next case to consider is when both powers are odd, when we have the integral of an odd power of tangent times an odd power of secant. Remember, when we had an even power of tangent times an even power of secant, the idea was to borrow secant squared from the power of secant. Now, in the case when both powers are odd, we're going to borrow one secant and one tangent from the powers to put with the dx. So this is a little informal, so let me explain what I mean. What I mean is that the integral of tan cubed x secant cubed x dx. I'm going to take one tangent and one secant to put with the dx. So what I'm left with is the integral of tangent squared x times secant squared x times secant x times tan x. Let me rewrite this where we have more space, that this is equal to the integral of tan squared x times secant squared x times secant x tan x dx. Now, when we let u be equal to secant of x, du is exactly equal to this secant x tan x dx that we have right here. So the integral we want to solve is now equal to the integral of tan squared x times u squared du. And remember, in the previous case, we used this identity that secant squared x equals tan squared x plus 1. So the idea is the same. Now we're just going to move the 1 to the other side. Tan squared x equals secant squared x minus 1. So let me pause and rewrite that and do the rest of the integral. Remember, our goal was to compute the integral of tan cubed x times secant cubed x dx. We borrowed a secant from the power of secant and a tangent from the power of tangent to put with the dx. We now let u equal secant x. So du is secant x tan x dx. We get the integral of tangent squared x times u squared du. And we're going to use the identity that tan squared x equals secant squared x minus 1, which in this case is u squared minus 1. So the integral we want to solve is the integral of u squared minus 1 times u squared du. We expand the u squared. We get the integral of u to the 4th du minus the integral of u squared du, which is 1/5 u to the 5th minus 1/3 u cubed plus c. And we substitute back in u equals secant x, and that gives us what we were looking for. So that's the key idea. When both powers are odd, we're going to borrow one secant and one tangent from those odd powers. So I'll pause and erase, and I'll say a few things about the last remaining case where one power is even and one power is odd, and then emphasize some things for you to remember. The final case to talk about is when one power is even and one power is odd. For example, maybe you have something like the integral of tangent of x, tangent to the first, 1 is odd, times secant squared x, 2 is even. So it's one power odd, one power even. This example is very simple. You let u equal tangent of x, so du equals secant squared x dx, and the integral that we want is just equal to the integral of u du, which is 1/2 u squared plus c, which is 1/2 tangent squared x plus c. So sometimes these integrals can be pretty easy. This one in particular, you don't need to do anything first before applying u substitution. But if you change it just a little bit to the integral of tangent squared x times secant x dx, it's not so clear what to do. Still, it's an integral with one power even and one power odd, but you only have one power of secant, so you don't have a secant squared x dx to let u equal tangent x and do u substitution. If you borrow a tangent and a secant to put with dx, you would want to let u equal secant x, but then you need to rewrite tangent in terms of secant, which is not so clear. So I just want to emphasize that this is much harder. One idea would be to rewrite this. Well, we know that tangent squared x equals secant squared x minus 1. So what does that mean? So the integral that we want is equal to the integral of secant squared x minus 1 times secant of x dx, which is the integral of secant cubed x minus the integral of secant cubed x dx minus the integral of secant x dx. This one we know from the beginning of this video, but the integral of secant cubed is quite tricky. This actually works with integration by parts. Where you let u equal secant and dv be equal to secant squared x dx, but it's tricky. So what I want to emphasize is that this 1 power even, 1 power odd case, I do not expect you to be able to do examples of this type, things like the integral of tangent squared x times secant x dx. This will not come up on a quiz or an exam. Things like tangent to the 4th x times secant cubed x are even trickier. You don't need to worry about that. You should definitely know how to do both powers even when the power of secant is at least 2. That's a small technical thing because you want to borrow a secant squared x to put with the dx. You should know how to deal with when both powers are odd. And you should be able to recognize that an example like the integral of tangent times secant squared x dx is not so bad. But you don't need to know how to do every example. So this one really is more difficult. I would not ask you to do the integral of secant cubed x dx. So let me just pause and then emphasize the key things that go into taking the integral of powers of secant times powers of tangent. So just a quick recap. What are the main things to know about integrating powers of tangent times powers of secant? The key ideas are that since tangent squared x equals secant squared x minus 1, we can take an even power of tangent. Tangent of 2n, tangent to the 2n x, is secant squared minus 1 raised to the nth power. So you can take something like tangent to the 6th and rewrite it entirely in terms of secant. Same idea. Since secant squared equals tangent squared plus 1, any even power of secant, secant to the 2n x, is tangent squared x plus 1 to the n. So if you have a secant to the 8th power, you can rewrite it entirely in terms of tangent. We saw how to deal with the case when both powers were even. The idea was to borrow a secant squared to put with dx, and then let u equal to tan x in a u substitution. When both powers were odd, we borrowed a secant times tangent to put with the dx, and let u equal to secant x in a u substitution. And the final case, when 1 power is even and 1 power is odd, is quite tricky, and we would not expect you to know how to do problems of that type on an exam.